extensions, say K over F and L over F, are said to be isomorphic if there exists an isomorphism of rings but there's an additional condition that phi restricted to F is equal to the identity function from F to F. So for all practical purposes, two field extensions are thought of as the same if you can find an isomorphism of the larger fields which keeps the elements, which maps each element of the smaller field into the corresponding element of the smaller field in the other extension. Let's look at an example. Let's look at K1 equals Qt mod t squared minus 2. This we are familiar with. T squared minus 2 is an irreducible polynomial, and so this ideal t squared minus 2 is a maximal ideal in Qt, and so Qt mod t squared minus 2 is a field and it contains Q. And let's construct another one, K2, and let's say this is Qt mod different polynomial t squared minus 2t minus 1. So this again is an extension over Q. And let's see if we can figure out whether these two extensions are isomorphic or not. Now on the face of it, they both have if you think of these as vector spaces over Q, they both have degree 2, so they could be isomorphic. Now we already have some understanding of this first field extension. We know that if you take Qt mod t squared minus 2, this is isomorphic to Q root 2 over Q. Why? Well, you just take the map phi bar of root 2. We saw that this gives rise to an isomorphism, and the way we defined it, the elements of Q go to the elements of Q because they just correspond to constant polynomials on this side. So this is an isomorphism. So this is K1. And what about K2? So let's just see what the roots of this polynomial t squared minus 2t minus 1 are. Well, if you just think about it, the roots are t equals 2 plus or minus square root 4 plus 4, 8 by 2, which is 1 plus or minus root 2. Okay, so in a similar manner, we can think of this K2 as Qt mod t squared minus 2t minus 1, but using the map phi bar, say 1 plus root 2. This goes to Q1 plus root 2. And this is an isomorphism over Q. But of course, Q root 2 is the same as Q1 plus root 2. Why is that? Well, if you have a field that contains root 2 and it contains Q, then it must contain 1 plus root 2. Conversely, if you have a field that contains 1 plus root 2 and contains Q, then it must contain root 2. So these are actually the same. Every field that contains Q and root 2 is also a field that contains Q and 1 plus root 2 and vice versa. And so we have that K1 and K2 are isomorphic over Q. We have this isomorphism which we can call let's say phi bar 1 plus root 2 circle phi root 2 bar inverse is an isomorphism from K1 to K2, and these are isomorphic over Q. Now suppose we have two field extensions, let's say K over F, and we have an element alpha here, and another field extension L over F, and element beta over here. So then we can talk about the field F alpha, and we can talk about the field F beta, which lies over F. So then in general, it's not very easy to figure out whether or not F alpha and F beta are isomorphic over F. But if you look at a slightly more restricted notion of isomorphism, then there's a very beautiful and simple answer. So that's the next theorem. So now suppose we have this situation where we have alpha in a field extension over F, beta in a field extension L over F, and alpha and beta are isomorphic, are algebraic. See, if alpha and beta are both transcendental, then of course F alpha is isomorphic to the field of rational functions over F. F of beta is also isomorphic to that same field, and so F alpha is isomorphic to F beta. And if alpha is algebraic but beta is transcendental, then F adjoint alpha is a finite dimensional vector space over F, whereas F beta, when beta is transcendental, is going to be infinite dimension. And so we know that F alpha cannot be isomorphic to F beta. So the only interesting case for the isomorphism question is when alpha and beta are algebraic. Okay, so the statement is that then there exists an isomorphism phi from K to L. So I'm going to draw it like this. So this means that phi is an isomorphism from K to L, but when restricted to F, phi is the identity. So it's an isomorphism of extensions, not just a ring isomorphism. But we're going to add an additional condition such that phi of alpha is equal to beta. Now once you add this condition, this decision problem becomes much easier. Then if and only if the irreducible polynomial of alpha over F equals the irreducible polynomial of beta over F. So when you put this additional condition that phi must map alpha to beta, then this problem becomes much simpler. And we'll see the reason why this particular problem is more interesting, is very interesting when we study Galois theory. So, so here's the proof. So to start with, let's assume that alpha and beta have the same irreducible polynomial over F. So suppose Pt belongs to Ft is the irreducible polynomial of alpha as well as beta over F. So then we have Ft mod Pt. On the one hand, this phi alpha bar gives an isomorphism to F alpha, phi beta bar gives an isomorphism to F beta, and these are all isomorphisms over F. And under this isomorphism, T goes to alpha. Under this isomorphism, T goes to beta. And so now if you take phi beta bar circle phi alpha bar inverse, then this is an isomorphism from F alpha to F beta over f with phi of alpha. Well, alpha goes to t, t goes to beta, equal to beta. So that proves one way. And for the converse, suppose that alpha has a reducible polynomial pt over f, and suppose that we have an isomorphism from f alpha to f beta. Is an isomorphism. With which takes alpha to beta. Now we have from ft we have the map phi alpha, the substitution map, to f alpha, and if you consider the map phi circle phi alpha, this is a homomorphism from ft to f beta, and this takes t to beta. Since it's a ring homomorphism, it also takes an t to the n plus a1 t plus a0 to an beta to the n plus a1 beta plus a0. So this gives rise to a map from ft to f beta, but you recognize this as the map where you're substituting for each polynomial the variable t to be beta. So what we have is that phi circle phi alpha is just phi beta. So the irreducible polynomial of beta over f is the kernel of phi circle phi alpha, but that's the kernel of phi alpha because phi is an isomorphism, but this is the generator of the kernel of so the ideal generated by the irreducible polynomial beta over f is this, but this is the ideal generated by pt, and so pt must be the irreducible polynomial of beta over f. An important property of isomorphisms of extensions is that if you take an element in one extension with a certain irreducible polynomial and you map it under an isomorphism to another field extension, then its image will have the same irreducible polynomial in the second extension. Let me state this precisely. Suppose phi from k to k prime over f is an isomorphism of field extensions. And suppose alpha belongs to k is a polynomial, is an element such that, and f is a polynomial in ft are such that f of alpha is 0. Then f of phi alpha is also going to be 0. This is rather straightforward. So let's just look at f of phi alpha. So let's say that f of t is the polynomial a n t to the n plus dot 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 plus a1 t plus a0. Then f of phi alpha is a n phi alpha to the n plus dot 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 plus a1 phi of alpha plus a0. Now an minus 1 up to a0, these are all elements of f. So phi of ai is equal to ai. So I can write this as phi of an, phi of alpha to the power n plus dot 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 plus phi of a1, phi of alpha plus phi of a0. So now we are applying phi to all the terms here, and they are just sums and products. So because phi is a ring homomorphism, this is the same as phi of an alpha to the n plus a1 alpha plus a0, which is just phi of f of alpha, where that is phi of 0, which is 0. That's the proof. Now let's look at an example. So consider the polynomial pt equals x cubed minus 2. So this is an irreducible polynomial in Qt. This polynomial has no rational roots. What are the roots of this polynomial? So let's say alpha equals cube root of 2, and let's say zeta is equal to e to the 2 pi I over 3. So this is cube root of 1 in the complex numbers. Zeta cubed is equal to 1. Then the roots of pt are in the complex numbers alpha, alpha zeta, and alpha zeta squared. So we have three fields. We have q alpha zeta, and q alpha zeta squared. And each of these elements, alpha, alpha zeta, and alpha zeta squared, they all have the same irreducible polynomial over Q, namely the polynomial x cubed over 2. X cubed minus 2. X cubed minus 2 is the irreducible polynomial of all these three elements over Q, and therefore these are all isomorphic over Q. These three extensions are isomorphic over Q. But notice that Q alpha is a subfield of the real numbers, whereas Q alpha zeta is not a subfield of the real numbers, and Q alpha zeta squared also is not a subfield of the real numbers. And so this means that if we want to think about these field extensions properly, it's important to sort of free them from the context of the real numbers and think of them as sort of abstract objects. And this is where the notion of isomorphism of extensions comes into being. So an abstract property of a field extension is something that's invariant under field isomorphism. Being a subfield of the real numbers is not such a property.